So this is a recent work. It's currently done in collaboration with my supervisor Punnabrata Pradhan, and this is the reference. So active particle or self-propelled particle, as we all know, so they have the ability to move ballistically with some velocity, say v, in a randomly chosen direction, and it persists the journey up to a certain time, and there is a typical time which is the persistence time. So this is the tau p, and that is connected with the rate 1 by gamma. So gamma is the rate at which it reorients to a new direction, and since in between such two successive reorientation they move ballistically, so one can associate a length scale which is the persistence length, and these three quantities are related in this fashion. So each particle, they are actually an energy source, so they continuously consume energy as well as dissipate at the microscopic scale. So these systems violate detail balance at the microscopic level. Okay, so the system that we are interested in are interacting self-propelled particles. So in our system there are many particles, many such active particles that are interacting with each other. So such systems are ubiquitous in nature. So for instance, in insect swarm, fish schools, bacterial colony, they are the examples of such systems. So there, this interaction and persistence, so interaction among the particles and persistent nature, so they are the two main ingredients in such systems, and their intriguing interplay between them gives rise to various collective phenomena which is not present in their equilibrium counterpart. So here I am going to focus on one such phenomenon, which is the anomalous transport. So which is defined as the transport of any observable, so whose mean square deviation grows non-linearly with time. So this is actually an example of anomalous characteristics of anomalous transport, and another one is the non-Gaussian spread. So these two can be coexist. I mean, they can be simultaneously present in such in any systems. Well, so these are the two such references where they actually reported these anomalous characteristics. They are basically super diffusive transport. First one is Cavania's nature. So here they are actually they have reported for inertial swarm of insects. And the second one in the context of active single file transport. So their super diffusive transport is reported. I mean, they are done by Abhishek's group. So it's Prithadola is and et al. So this is the reference. Okay. So in our model, in our systems in general, so particle number is a conserved quantity. So then if we just perturb density profile, then at large spatiotemporal scale, it should be governed by a continuity equation, and this is the equation. And the relaxation should be governed by this collective or bulk diffusion coefficient. Now this diffusion coefficient has non-trivial information about the interaction and persistence. That's why they are parameterized by these two variables, rho and gamma. So we have taken the large system size in our systems. We have taken the large system size limit first, and then tuned to larger activity, which is by tuning this gamma tends to 0, the persistence rate. And this limit actually, I mean, distinguishes the earlier work on active lattice gases, where the hydrodynamics at the exact level as well as the fluctuating level were done in these two references. So they are actually the persistence rate scales with system size. So that's why, I mean, these two limits were taken simultaneously in that model, but our model is different. However, in Dandekar, R. Rajesh and Shubhadeep Chakraborty's paper, they calculated similar quantity, bulk diffusion coefficient, but for different model, it's directed mass transfer model, and they have obtained that at very low activity persistence rate, which is at large activity, this diffusivity scales as persistence rate, but it is independent of density to a leading order. Okay, so I have talked about interaction, but I haven't here actually mentioned the type of interaction. So in our model, there is no velocity alignment interaction. So there are only hardcore repulsion. So they interact via excluded volume interaction. Now, I argue that in the limit, when limit of strong persistence, which is obtained by gamma tends to 0, and dilute limit when rho tends to 0, then there are two relevant length scales in the system. The first is the activity induced length scale, which is the persistence length, which is defined by V over gamma. V is the self-propulsion speed. And this interaction induced, now since particles are interacting, so they cannot move freely, so they will interact. So there are the relevant length scale in that context would be mean free path, or you can say mean gap size. So this is 1 over rho. As long as the system is dilute, it is 1 over rho at arbitrary dimension. So one can then immediately construct a length, scaling variable, which is a ratio of these two length scale. And actually, it actually quantitatively quantitatively describes the interplay between this interaction and persistence. So when psi tends to 0, the system is in the non-interacting, truly non-interacting limit, but psi tends to infinity corresponds to strongly interacting. So it's interesting, even though the system is in the dilute regime, they can be strongly interacting also. So then if you can construct such scaling variable, then it is expected that any physical quantities that incorporates the effect of this activity as well as the interaction can be written as a scaling variable. It should satisfy a scaling relation like this, where actually v square by gamma has a dimension of diffusivity, and any non-trivial effect of persistence and interaction, they are encoded in this scaling function. So so this f psi actually is model dependent, otherwise v square by gamma is normal. So at non-interacting, so now there are two limiting cases. At non-interacting regime, this we know that the diffusivity should grow as should be v square by gamma. So that means in that case the f psi is constant. And at the strongly interacting regime, when this diverges, scaling variable diverges, then actually what happens, then particles form clusters. So in that case, the diffusion takes place at the time scale of gamma, so which actually suggests that the f psi should grow as 1 over psi square. So these are the two limiting cases where f psi at one end it is constant, and at the other end it is 1 over psi square. So this is actually something, these are the main result, and I haven't yet talked about any microscopic details of the model and any dimension. So this holds for arbitrary dimension and for a class of active matter systems. So now I will verify this claim for two models of active systems. So the first model is the typical run and tumble particles. It's in one-dimensional, defined on a 1D lattice. So their particles are, the particles are associated with spin that directs the local drift of each particle. So at rate 1, a particle performs persistent jump across the spin direction, provided the destination site is vacant. However, spin of each particle flips, so this is called tumble. So they flips at rate gamma. So then what happens, in between two spin flips, which is called tumble, a particle performs long range motion. So this long range motion actually motivates us to define this model, this long range lattice gas model. So here particles are hardcore, but they do not have any intrinsic spins, but they can perform long range motion. So but this the long hop length can be a variable, and that can be drawn from an arbitrary distribution. So we chose this distribution to be exponential with a characteristic length scale to be LP, which is the persistence length of RTP. In that way, we can compare this model with the RTP model. Well, the first model actually, it's more or less it's the same model studied in this paper, Soto-Golestanian in PRE 2014, and a variant of this model is the famous fragmentation aggregation model studied in Majumdar-Krishnamurthy Barma's PRL, and another variant is studied where we studied the hydrodynamics of this model, a variant of this model anyway. Okay, so now enough. So now actually we want to calculate this diffusivity. So this long-range lattice gas model is a quite special model, because although it has non-trivial long-range correlation, but one can handle this model. Actually, we can calculate, almost everything analytically. So this is the, so we calculate this diffusivity analytically. So there the quantity of interest is the time integrated current. So time integrated current is the current across, if you just consider a bond, so what is the current up to a time t? So using microscopic, so now interestingly the system is non-trivial, but it satisfies a gradient property. So then if you microscopically write down the update equation of this current, so that instantaneous current, which is the time rate of change of this integrated current, can be written in this fashion microscopically. Okay, so here the coefficient is our desired diffusivity, and this has the following form. So everything actually in this particular expression, it's a long expression, so everything is known except this PG. PG is the gap distribution or free path, how the free path is distributed. So that is so far unknown. Okay, so but we have observed that this this gap length or the free path, it has an exponential tail, and from simulation we have seen that it has a quite robust scaling. This similar scaling is observed for long range lattice gas in RTPs, in 1D ABPs also. So anyway, so this is the scaling form. So if we just plug them in this in this expression, and if you anyway, yeah. So if you just plug them in this expression, and if you perform this asymptotic scaling, I mean asymptotic analysis in the limit rho tends to 0 as well as this gamma, that is the flipping rate, goes to 0, then we recover the scaling relation where the scaling function looks like this. Now, well, and we also have this form of the scaling function. This is this scaling function g psi, which actually for another variant. I mean, it's a dual for the dual model of the corresponding to this long range lattice gas. We have this g psi is nothing but the gap is nothing but the mass distribution function. So we have this idea about this g psi. So if we just plug them in, then we get this expression for the f psi. This is the scaling function corresponding to the bulk diffusivity. So this is the main result of our paper. This is a reference. Okay, so this is for the long range lattice gas, but for the RTPs, unfortunately we couldn't do analytics there, but we calculate the similar diffusivity numerically. So using the method that was prescribed in this famous Katz-Lewis-Pons paper 1984. So there actually they prescribed that if you just initially perturb the system sinusoidally, and if the perturbation is weak enough, so this is the background density rho naught over which a sine perturbation is applied. So, and we are considering the weak perturbation, so the background density is much larger than the perturbation height. Then at the late time, this amplitude will decay, and it will relax exponentially with the relaxation, and the relaxation rate directly gives me the diffusivity of the system. So for instance, this is a typical profile at various times. So this is suppose the initial time. I mean at time tau is of the order of L square, so it's scale time. So it's at 0.02. At some later time, the amplitude decays. Again, as time goes on, it's decaying, and the decay actually it is an exponential decay, and the slope gives me the relaxation rate. And from that, the diffusivity can be calculated. We just perform the same experiment for various parameter values and obtain the diffusivity for across various density as well as tumbling rate regime. Okay, so this is the parameter dependence, how they behave as a function of the density as well as the activity as well as the tumbling density. So these two plots actually they correspond to, first one is for RTPs and another one is the LLG. So up to a time scale they follow, qualitatively they behave qualitatively in a similar way. So yeah, so actually there is some non-monotonicities there. So that yesterday I think Professor Ganpati actually told about this. So as a function of activity, it decays monotonically. It has a non-monotonic behavior. So again, this is due to the non-trivial interplay between interaction and persistence. So but as a function of density, there is no clear relation, but it has a power law type tail. But the exponent varies across the various parameter regime. So at some point there is rho to the -2 tail, but at some point there is rho to the -1 tail, and somewhere in between also. So now if we just scale all the parameters suitably, then we obtain the scaling collapse. So this one is for RTPs, so this is the simulation points, and for LLG this is also the simulation results, and we have the scaling function f psi for LLG, and this is the thick line is the scaling relation, and our result matches surprisingly quite well. Unfortunately, we don't have the expression of f psi for RTPs because we don't have analytical solution to that problem. Okay, so far actually we have the result for diffusivity. Now the thing is that how to characterize anomalous transport from this diffusivity, from the information of diffusivity. So we just ask this question. So how does suppose we have an initially localized density profile and it relaxes. So it's 13 minutes or 18?
15 minutes or over.
Oh, I see. Okay, fine. I will conclude. So yeah. So suppose we have an initially localized distribution, and it should relax, and it is relaxing over an empty background. So then, in the time regime, which is much larger than the activity scale, but it is much smaller than the L square, typical system size L square. So then, what happens? The system, the density profile is heterogeneous. So you have to incorporate the density dependence in diffusivity. But and we have seen that there is, power law type tail in diffusivity. So using this expression for diffusivity, we can solve the diffusion equation with the scaling ansatz, where we have calculated that there exists a relation between this growth exponent omega and this exponent alpha, and this is like this. So omega is 1 over 2 minus alpha. This alpha now actually always greater than 0. It's between 0 and 2. So then, which means that omega is always greater than half. So that means the growth exponent is always greater than half. That means it's a super diffusive transport. So from it is surprising that so from diffusion equation, starting from diffusion equation, we get a super diffusive scaling, but it is the nonlinear diffusion. That's why we get this super diffusive transport. Now, if we just tune the parameter values and we just fix our system in such a way that alpha is 1, that means d is 1 over rho. Then actually omega is 1. So that means the ballistic scaling. So and the corresponding solution looks like this. So and we this is the plot. I mean, we scale the position with time. This is the x by ct scaling, and we see that the data collapses quite well, and this line is the analytic result. So this is also matching. Okay, and also at very large time, when the time is of the order of L square, it reaches the diffusive scaling, and this is the result. I mean, I scale the system size, space as I by L and time by T by L square, and at different system sizes, this data actually scale data falls quite well. So that means at very large time, and the time is of the order of 0.2 L square, so it's very large. So it reaches this diffusive scaling. Okay, and also so far the results were in 1D, but similar scaling is observed in 2D also. This is the results for 2D LLG as well as this RTP. So I just scale rho by gamma, and this is the scale diffusivity. So similar scaling is observed also in hard rod models also in 1D. So anyway. So that's it. So actually, and now it's time to conclude. So we argued that the bulk diffusion coefficient that depends on a single, effectively single scaling variable, which is the psi at very low density and tumbling rate. So, and the scaling function we have calculated for 2 paradigmatic models, and in different density regimes, we have seen that the transient relaxation is super diffusive, and even in certain cases ballistic. And it is independent, the argument is independent of dimension and microscopic details. So yeah, thanks.